Welcome to Ask and Learn.
So for problem 15.184, we've been given the velocity, the vector velocities for points A and D, and we've been asked to find the angular velocity of the rolling ball and the velocity of point C, which is the center of the ball. In order to do this, we have to relate the vector velocities for point A and D with the angular velocity and the velocity of the center. This can be done using equation 15.43 from the textbook. You will see right away why I'm writing the one for point D first. This notation here is the relative position vector for point D relative to C. And now the same for point A. It's the cross product of the angular momentum, of the angular velocity with the relative position vector of A with respect to C. Now, in order to get the angular velocity, we can do this little trick and subtract the two equations, and we get the vector difference between velocities Vd minus Va. And this expression here, for which if we use the linearity property of the cross product, we can write as this vector difference, for which though if we use the definition of these relative position vectors, it can be simplified hope this is clear, and we get the vector difference of velocities from point D to point A equals the cross product of the angular velocity to this difference of the position vectors of points D and A. So now we have to calculate explicitly the values for these two vector differences in order then to solve for the angular velocity. Let's begin with the velocities. This must be quite straightforward. If you do the calculations, this is just 4.8 plus 4.8 g hat 3.6 g hat. And now if we check from the drawing, the position vector for point A from the origin is just this expression with R, the radius of the ball, which equals to 109 millimeters. And similarly for point D, this is the expression. Therefore the difference is just immediately plus rj hat. Okay, now we need to calculate the cross product of the angular velocity times rd minus ra. In order to do this, we can do this using indiscriminant form. But before we begin, we might be able to see simplification here. The rolling ball is rolling on the xz plane. So the angular velocity must be parallel to this plane. So actually there's no y component for the angular velocity. And this makes our lives easier, and I hope it is clear that the result of this determinant is the following. And if we compare now to the vector difference of velocities Vd minus Va, which was this one, we can deduce that the x component of the angular velocity is 3.6 over r, which is about 33 radians per second, and the z component is minus 4.8 over r, which is about 44 radians per second. So now that we have the full value for the angular velocity, let's write it again for convenience in terms of r. We can go back to one of the initial equations relating velocity of one of the points to the angular velocity and the velocity of point C. Let's pick for convenience the one for point D. Again, this is the relative position vector, point D with respect to C. Okay, and now we know the angular velocity. We can calculate this one. We do know this one, and we can get that one. Let's express this again. In terms, in the form of a determinant. and this is r, just r, because the position of d relative to c equals the position of d from the origin minus the position of c from the origin, which is just r j hat, as you can see from the drawing, resulting to just r j hat. I hope you can see the result of this determinant. Is this one, resulting eventually the velocity of point C being simply 4.8 I hat plus 3.6 k hat meters per second as the units. And that was it.